Hi everyone, welcome to my channel. In the video covering flip-flop theory, basic SetClear flip-flops, we ended with the logic symbols for both a NOR gate type SetClear flip-flop and an AND gate type SetClear flip-flop with their accompanying truth tables. But it was mentioned that flip-flops can have multiple inputs, and so far we have a set and a clear. But we're going to introduce a third input, and that's a clock input. Now, most digital systems operate as synchronous sequential systems, and what this means is that the sequence of operations that takes place are all synchronized by a master clock signal. So when we look at these truth tables here on how to control the cue output, these still apply, but they only take effect in coordination with the clock signal. So most digital systems operate as synchronous sequential systems, and what this means is that a sequence of operations are synchronized by a master clock signal. And that master clock signal is usually a square wave with a 50% duty cycle. So the clock signal is usually a square wave with a 50% duty cycle, and what this means is that in one cycle the square wave is going to be on half the time and off half the time, or a logic 1 and a logic 0. So if we go from this edge to this edge here, in that amount of time, it's half on and half off. So the clock signal is going to be the triggering signal, and the set and the clear are the control signals. And the trigger is not the whole square wave. It's usually going to be either the rising edge, where it goes from 0 to 1, or the falling edge of the square wave, where it goes from 1 to 0. So if we look at the logic symbol for a set and clear flip-flop again, we can now add a clock input, CLK. So if the flip-flop is triggered by the leading edge or the positive going edge of a clock signal, there will not be a circle on the input. But if it is a flip-flop that triggers on the negative going or the falling edge of the clock signal, that'll be designated by a small circle on the clock input. So these truth tables for the set and clear flip-flop still apply. And the set and clear are the controls that control what the output of Q is going to be, but the clock is the trigger. So this does not happen until the clock, either the rising edge or the falling edge, triggers the event. So the set and clear are the control inputs which control which direction the Q is going to go to, but it's not going to happen until the clock signal triggers that, whether it's the rising edge, the leading edge of the clock signal, or the falling edge of the clock signal. So if we had a NOR gate type set clear flip-flop and we applied control signals set and clear along with the clock signals, the timing would look something like this, and then we show what the output is at Q. This still is the same, it's just that the Q responds only on the leading edge, in this case, of the clock signal, in conjunction with the two control signals on the set and the clear. So on each of these leading edges, I've hashed out a line. So if we have the set control, and this is 0 and this is a 1, and initially it's at 0, and then it goes to a 1. And if the clear is 0, so here we have the clear is a 1 and here's a 0, and it's a 0. At this point here we have set equal to 1, clear equal to 0. So Q will go to 1, but it goes to 1 at the leading edge of the clock signal. So here, if we have Q Q will go to the 1. So this is 0 and this is 1 at the leading edge of this clock signal. And it will stay there, and it will only have an opportunity to change if the set and the clear changes state at the next leading edge of the next clock signal here. So if the set was to go to 0 again and then go back up to a 1 and then go down to a 0, this Q output is not going to do any responding to the changes in the levels on the set and the clear at this point. So if at the next rising edge of the clock pulse the set is 0 and the clear still is 0, the Q will not change, because a 0 and a 0 on the set and the clear is a no change condition. So the next chance for it to change is on the next leading edge. So if at this point here the set is now 0 and the clear is now at a 1 state, that will change Q to 0. So at this leading edge here, the Q output will then go to 0. And let's see if we have this go high again, and it is high at that stage there, and the clear goes low again. Here we have the set high and the clear is low, so Q will equal 1 again, so the output, the Q, will go high again. So you can see that these are the set and the clear are control inputs, and the clock is the trigger. But now that we have a clock signal that's triggering these events to respond to the control inputs at these times here, we now have timing parameters that we have to consider. And what we need to do is make sure that the set and the clear control signals are stable for a certain period of time before the clock signal and remain stable for a period of time after the triggering portion of the clock signal. So if we had a SetClear flip-flop that responds to the negative going edge of a clock pulse, and this is the set input. The set input, if it was going to be set to 1, it has to be at a 1 for a period of time, TS, or setup time, prior to the falling edge. So it has to be at a stable condition for a certain period of time before the triggering edge of the clock pulse. And the set has to stay at that stable position also for a period of time after the clock pulse, which is the hold time. So we have TS, which is the amount of time that the signal has to be, the control signal has to be stable prior to the triggering edge of the clock pulse. And we have TH, which is the hold time, which is the amount of time that the control signal has to remain stable after the triggering edge of the clock pulse. So setup time is the amount of time that the set or the clear input levels must be held stable prior to the occurrence of the triggering edge of the clock input in order for proper triggering to occur. The hold time is the amount of time that the set and clear inputs must be held stable after the triggering edge of the clock input occurs. So even though I've spent a lot of time describing the operation of SetClear flip-flops, you're really not going to come across this type of flip-flop. There's a more popular flip-flop called the JK flip-flop, and it does everything a SetClear type flip-flop does, with the addition that it doesn't have this ambiguous state. So the set and clear has the disadvantage of it has this illegal or ambiguous state, you can't predict, you're supposed to avoid this condition. The JK flip-flop takes advantage of this condition where the set and the clear are 1, and there's a new mode of operation called toggle mode. And when the set and the clear are both 1, each time the trigger edge of the clock pulse occurs, the Q output will toggle to the opposite state. So if it's a 1, when the triggering edge of the clock pulse occurs, it'll go to a 0, and if it's already a 0, it'll then go to a 1. So the JK flip-flop does everything a SetClear flip-flop does, plus it has this toggle mode of operation. That's why it's more popular. So the JK flip-flop is a more versatile flip-flop. It does everything that the set and clear type of flip-flop does, except it does away with the ambiguous condition. It makes use of the condition where if you have both inputs set to 1, you now have a toggle mode of operation. And what this means is that with the J equal to 1 and the K equal to 1, the Q output will toggle to the opposite level that it's currently in on the triggering edge of the clock pulse. So if prior to the triggering edge of the clock pulse, in this case the leading edge or positive going edge of the clock pulse, if Q is equal to 0, it'll toggle to 1, and if Q is equal to 1, it will toggle to 0. So it can do everything that a SetClear type of flip-flop can do, with the added benefit of having this toggle mode of operation. And you can have a flip-flop that responds to the negative going edge of a clock pulse, and it would be designated with a small circle on the clock input. So if we put a 1 on J and a 1 on K, we are now in the toggle mode of operation. If we have a clock pulse with a 50% duty cycle, and we start off with Q equal to 0, on the first leading edge, if we remove this circle, pretend this responds to the leading edge of a clock pulse. If we start off with Q equal to 0, it will toggle on the leading edge of this clock pulse. So it is now a 1. On the next leading edge of the clock pulse, it will toggle to 0. So it is now 0. And on the next leading edge, it'll toggle back to 1 again. So this is 0 and 1. Oh, and the leading edge right here, it'll toggle back down to 0. Now, if you've noticed, what has happened, if this is the clock pulse here with a 50% duty cycle, and we're now looking at the Q output is now half of the frequency of the clock signal. So the JK type of flip-flop has extensive use in counting, in binary counting, and also frequency division. So that's another one of the benefits of the toggle mode of operation of the JK flip-flop. So if you go through this Texas Instruments TTL data book, you won't actually find SetClear flip-flops. Here is a 7476, and this is a dual JK flip-flop. Again, the JK flip-flop can do anything the SetClear flip-flop can do, with the added benefit of the toggle mode of operations. So the 7476 actually has 2 flip-flops in a 16-pin dip IC here. And if you look here with the clock symbol, if we have a high on the J and a high on the K, we're in a toggle mode of operation. There's two additional inputs on this device, a preset and a clear. We could talk about those at another time. But let's break out the Heathkit Digital Trainer and hook up a couple of these 7476 dual JK flip-flops. So here I have a couple of 7476s. Those are dual JK flip-flop devices. Zoom in there before I wire them up. Now if we look in this data book, a lot of the gates, the logic gate ICs, the ground was pin 7 and the power or VCC was pin 14. That's not the case for the 7476. Here we have VCC is pin 5 and ground is pin 13. So you can see there VCC and ground, and here are the pinouts for the two JK flip-flops. So first I'm just going to wire a single flip-flop, and then we'll go through the different levels on J and K, and then take a look at the toggle mode of operation with a 1 on the J and a 1 on the K. Okay, so I have one of the flip-flops of the 7476 wired up. I have a switch 1 and a switch 2. Switch 1 is the J input, and switch 2 is the K input, and I have L4 here, which I have connected to the Q output of the first flip-flop. And here I have a momentary switch that simulates a clock on the clock input. So this will trigger, this particular 7476 triggers on the negative edge of a clock pulse. So here it's at high, and then it'll go low, and that will trigger the flip-flop to change states depending on what levels are on the J and the K. Again, this is exactly like a SetClear flip-flop, except with the added benefit of a toggle mode of operation when J and K are both set to 1. So here we have 0 on the output. Q is equal to 0. And we have J equal to 0 and K equal to 0. And if we trigger, we set the clock pulse, the falling edge of a clock pulse, nothing happens. So we have a 0 and a 0 is a no change condition. So now if we set J equal to 1 and leave K equal to 0, on the next falling edge of the clock pulse, remember this is a clocked JK flip-flop. We've now introduced a clock input. This will light when it gets triggered by the falling edge of the clock pulse. So there it lights. So now if we set J equal to 0 and K equal to 1, Q will now go to 0 on the next falling edge of the clock pulse. And now it's 0. Now if we set J and K equal to 1, each time the clock pulse goes from 1 to 0 on the falling edge, it'll toggle to the opposite condition. So I'm manually being a clock signal here. So here we have a 0, so the next falling edge of the clock, this should go to 1. And then on the next falling edge of a clock, it should go to 0. So here we're in the toggle mode of operation with J equal to 1 and K equal to 1. Now I do have a clock on this, so if I was to take this and move it over to this clock here, it now is toggling on and off. Now if I take this and move it over to this LED, you can see the frequency that it's toggling at. And if I just go ahead and show you the frequency, it's at 1 Hertz, that the clock is toggling at, You can see here, visually it's hard to discern, but if I go like this, you can see the frequency that the clock is oscillating at by looking at the LED. And now you see that the output of Q on the JK flip-flop is half the frequency. So we've divided the frequency in half, but it is also counting. And because we have just 2 digits here in binary, it's able to count up to 3. So you can see here, if we wanted to count up to 4, we'd require another digit or a position. We only have the 2 LEDs. So it's counting up to 3, and then it's repeating. In the next circuit, I've wired up 4 JK flip-flops. I've tied all the J and K inputs high, and I've fed the Q output to the next JK flip-flop clock input. So Q0 gets fed into the second JK clock input. Q1 gets fed to the third JK clock input, and the Q output from the third gets connected to the clock input of the fourth JK flip-flop. And then I'm monitoring Q0, 1, 2, and 3 to the LEDs. Well, they're labeled on the trainer opposite direction, 1, 2, 3, and 4. But now you can see the counting. I've got the clock going into the clock of the first JK flip-flop, and that's at 1 hertz. So this gets divided as we go down the line here. So this is 1/2 hertz coming out of Q0, 1/4 hertz coming out of Q1, 1/8, and then 1/16 out of Q3, or the fourth JK flip-flop. So here I have 2 ICs, 2 7476s, and you can see here, you can think of it as dividing. Also, it is counting. So with 4 positions, we can count up to 15 in binary. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then it repeats. So to summarize, we've introduced the idea of a clocked input to a SetClear flip-flop in addition to the control inputs, and the clock triggers the control input to change the Q output either on the leading edge or the falling edge of a clock signal. And then we've introduced a JK flip-flop, which does away with the ambiguous state that the SetClear flip-flop has, and we have a new toggle mode where if we set J and K equal to 1, the flip-flop will toggle, Q output will toggle from 0 to 1 or 1 to 0 on the leading edge or the falling edge of a clock pulse. So the JK flip-flop can do everything that the SetClear type of flip-flop can do, except it has the additional toggle feature, and one of the uses of JK flip-flops are in counting, and where we feed the output of one flip-flop to the clock of the next flip-flop and proceed like that down the line, we can end up counting or also dividing a frequency. You can consider it as dividing also in addition to counting. So I hope you found this video interesting. Feel free to like, subscribe, and or comment, and thanks for watching.